So in order to solve a differential equation, to solve a, again the abbreviation Diff EQ, we use, well, how would I go from a derivative to the function it came from? Integral. We use integration. So to solve a differential equation, so you'll be given a derivative and they'll say solve it. What are they asking you to do? They're asking you to find the function it came from or find the antiderivative, use integration. Now what we're going to spend most of our time doing in the beginning of this section is verifying differential equations. So in other words, they're going to give us both a differential equation and the function that it came from, and they're going to say, could this function be the antiderivative? Could this be the derivative of this function? They're going to give you both of them and say verify. So it's like a proof. So work your way from one to the other. So to verify a Diff EQ, we can differentiate. We can use a derivative. All of a sudden I couldn't spell derivative. So the problems that we'll be looking at, the directions will say something like determine whether the function is a solution of the differential equation. And sometimes the differential equation will be given to you in the directions, and then you're supposed to compare that differential equation with each answer that they give you, or they'll just give you both. So for this one, for problem number 1, here they'll basically say, well, this is the one of them, and here's the other one. So how do you know if this is the way here's the directions and this is the problem? How do you know which one is the differential equation and which one's the solution? Because there's two things. Determine whether the function is a solution to the differential equation. So which is the function, which is the differential equation? How do you know that? It doesn't have a what? Y prime. A differential equation has a derivative in it. Okay? So you can tell which one is the differential equation. The differential equation is the one that has y prime or y prime prime. In fact, I mean, this means, what does the second prime mean? What? The derivative of the derivative, the second derivative. Okay? So we need to verify that this function right here could be a solution to this differential equation. So here's how we do this. We are basically going to use derivatives like we said up here. And so I'm going to start with this function right here, and I'm going to find its derivative. But I don't need its first derivative, I need its second derivative. And then I'm going to fit that derivative into this equation and see if it could possibly work out. So, first thing I'm going to do is I'm going to take the needed derivatives. Derivative or derivatives. Because sometimes the differential equation will only have y prime in it. So this is my function. I'm going to take the needed derivative. So y prime The derivative of sine is cosine of x, and the derivative of cosine of x, or the second derivative, is negative sine of x. Okay, so I took the necessary derivatives. Now what I'm going to do is I'm going to fit the derivatives, and in this case, derivative or derivatives, and the function into the differential equation. And this will make sense. We'll do more than one example. So the second thing I'm going to do is I'm going to fit these. So I've got the function and the second derivative is what I need. I'm going to fit those using substitution into the differential equation that I'm given. So I start with my differential equation now. And I say, well, what was the second derivative of sine x? Negative sine of x. And what is the actual function? Y was equal to what? Sine. So negative sine of x minus sine of x. Does that question mark equal 0? No. So this is actually negative 2 sine of x. That does not equal 0. So what can we say? Is this a solution? Is this function, y equals the sine of x, a solution to that differential equation? Yes or no? No. Okay, so y equals sine of x is not a solution to y prime prime minus y equals 0. And it is definitely write-it in a almost complete sentence. Because just saying yes or no, I mean, this shows that you understood what the question was asking when you write the answer in this fashion, rather than just a yes or no answer. So this function is not a solution to that differential equation. Okay, so all we're going to be doing is looking at a few more of these examples. And you'll be seeing, well, I'll throw it at you at the third example. So let's take a look at another example, example number 2. We want to see, does y equals 4e to the negative x, does that fit into the same differential equation that we just looked at? So this is same differential equation we just had, and here's the function I want to see. Could this be a solution to this differential equation? So all I'm going to do is take this function and take a couple derivatives. So the first derivative, 4 times e to the negative x. Well, constant multiple rule, so the 4 is just going to sit there. What's the derivative of e to the u? E to the u times du, u prime. What's the derivative of negative x? Negative 1. So the derivative will be negative 4 e to the negative x. And the second derivative, okay, you've got the derivative of e to the negative x is basically all you're taking, leaving that negative 4 in front. So again, the derivative of e to the negative x is e to the negative x times negative 1, which will change it back to a positive 4. I really like the derivative of e to the x, because it's pretty much the same, just times the derivative of the exponent every time. All right, so now we need to fit these derivatives into our differential equation. This was step 1, taking the needed derivatives. Now I'm going to try to fit these in here and see if it's a true statement. That's really all you're doing. You're fitting them in and then seeing if the statement, if they equal 0. So I take my second derivative, 4e to the negative x, minus, okay, back to the original function, 4e to the negative x, and question mark, does that equal 0? Yes or no? Yep, it does. So 0 does equal 0. So what final statement would I make? Y equals 4e to the negative x is a solution to y prime prime minus y equals 0. That should not be a prime. All right, so I would like to see where I got this problem from. So example 4, we've got y equals negative cosine of x, natural log of the absolute value of the secant of x plus the tangent of x. And we want to verify that that is a solution to this differential equation, y prime prime plus y equals tangent x. And your book's actually nicer. They label the solution in the differential equation. But really, you need to be able to tell when looking at the problem, okay, you need to say, well, this is the differential equation. How do I know? Because it's got the derivative in it. And this is the, you can call it the solution. Okay? In other words, we had a function like this. We took its antiderivative. We probably had to do it twice. And we came up with this. We came up with this. So we want to verify, could this actually be the solution to this? So we do the same thing. We're going to take the necessary derivatives here. And it looks like we need to take 2 derivatives, and this looks like it is going to be fun. So the first derivative, we need to use what rule? Product rule and the chain. So the chain will be on the natural log of that, but this will be the product rule. So I'm going to have the first, which is negative cosine of x, times the derivative of the natural log of u. Might require u prime over u. So u prime will be the derivative of secant x, which is secant x tangent x, plus the derivative of tangent x, which is secant squared x, all over secant x plus tangent x. So that's first times derivative of the second plus second times the derivative of the first. What's the derivative of negative cosine x? It's the derivative of cosine x. Negative sign, make it a opposite, so it's positive sine of x. All right, so before I actually try to take the second derivative, this looks really bad, so I'm going to try to simplify this. What can I factor out of these two? I can factor out a secant x, and then I have basically secant x plus tangent x inside. Is it okay that I switch the order? Yeah. And then that, thankfully, cancels with the bottom. So that makes this cosine times secant, but what's the reciprocal of secant? 1 over cosine. So this is actually negative cosine of x times 1 over cosine of x, which will make that whole first messy thing change into what? Negative 1 plus, and I'm going to write the sine of x in front, sine of x times the natural log of the absolute value of secant x plus tangent x. Now that's only the first derivative. We still have to take another derivative. So again, we've got our first and second derivatives. We matched them up into this differential equation. We fit them in. The second derivative went here. The function went in here. And we're seeing, does that equal tangent of x? These two terms are the same but opposite signs, so they cancel. And yes, it does work out. So we can say that, and we could even go up here and, like, you know, cheat, maybe not cheat, but be lazy a little bit and say that